Probability distribution fitting, or simply distribution fitting, is the fitting of a probability distribution to a series of data concerning the repeated measurement of a variable phenomenon. The aim of distribution fitting is to predict the probability or to forecast the frequency of occurrence of the magnitude of the phenomenon in a certain interval. There are many probability distributions, of which some can be fitted more closely to the observed frequency of the data than others, depending on the characteristics of the phenomenon and of the distribution. The distribution giving a close fit is supposed to lead to good predictions. In distribution fitting, therefore, one needs to select a distribution that suits the data well. Selection of distribution. The selection of the appropriate distribution depends on the presence or absence of symmetry of the data set with respect to the mean value. Symmetrical distributions. When the data are symmetrically distributed around the mean while the frequency of occurrence of data farther away from the mean diminishes, one may for example select the normal distribution, the logistic distribution, or the student's t-distribution. The first two are very similar, while the last, with one degree of freedom, has heavier tails, meaning that the values farther away from the mean occur relatively more often. The Cauchy distribution is also symmetric. Skewed distributions to the right. When the larger values tend to be farther away from the mean than the smaller values, one has a skewed distribution to the right. One may for example select the log normal distribution, the log logistic distribution, the Gumbel distribution, the exponential distribution, the Pareto distribution, the eyeball distribution, or the Fra-Copyright-Chet distribution. The last three distributions are bounded to the left. Skewed distributions to the left. When the smaller values tend to be farther away from the mean than the larger values, one has a skewed distribution to the left. One may for example select the square normal distribution, the inverted Gumbel distribution, or the Gompertz distribution, which is bounded to the left. Techniques of fitting. The following techniques of distribution fitting exist: parametric methods, by which the parameters of the distribution are calculated from the data series. The parametric methods are, method of moments, method of L moments, maximum likelihood method. Regression method, using a transformation of the cumulative distribution function so that a linear relation is found between the cumulative probability and the values of the data, which may also need to be transformed, depending on the selected probability distribution. In this method, the cumulative probability needs to be estimated by the plotting position. Generalization of distributions. It is customary to transform data logarithmically to fit symmetrical distributions to data obeying a distribution that is positively skewed. See log normal distribution and the log logistic distribution. A similar effect can be achieved by taking the square root of the data. To fit a symmetrical distribution to data obeying a negatively skewed distribution is minimum, as is done in Cumfrec. The generalization enhances the flexibility of probability distributions and increases their applicability in distribution fitting. Inversion of skewness. Skewed distributions can be inverted by replacing in the mathematical expression of the cumulative distribution function by its complement, f equals 1f, obtaining the complementary distribution function that gives a mirror image. In this manner, a distribution that is skewed to the right is transformed into a distribution that is skewed to the left and vice versa. The technique of skewness inversion increases the number of probability distributions available for distribution fitting and enlarges the distribution fitting opportunities. Shifting of distributions. Some probability distributions, like the exponential, do not support data values equal to or less than 0. Yet, when negative data are present, such distributions can still be used, replacing x by y equals xm, where xm is the minimum value of x. This replacement represents a shift of the probability distribution in positive direction, that is to the right, because xm is negative. After completing the distribution fitting of y, the corresponding x values are found from x equals y plus xm, which represents a back shift of the distribution in negative direction, that is to the left. The technique of distribution shifting augments the chance to find a properly fitting probability distribution. Uncertainty of prediction. Predictions of occurrence based on fitted probability distributions are subject to uncertainty, which arises from the following conditions. The true probability distribution of events may deviate from the fitted distribution, as the observed data series may not be totally representative of the real probability of occurrence of the phenomenon due to random error. The occurrence of events in another situation or in the future may deviate from the fitted distribution, as this occurrence can also be subject to random error. A change of environmental conditions may cause a change in the probability of occurrence of the phenomenon. An estimate of the uncertainty in the first and second case can be obtained with the binomial probability distribution using, for example, the probability of exceedance P and the probability of non-exceedance Pn. In this case there are only two possibilities, either there is exceedance or there is non-exceedance. This duality is the reason that the binomial distribution is applicable. With a binomial distribution one can obtain a confidence interval of the prediction. Such an interval also estimates the risk of failure, that is the chance that the predicted event still remains outside the confidence interval. The confidence or risk analysis may include the return period t equals 1/p as is done in hydrology. See also, density estimation. References